Hi, I'm Alex Brown. I'm a biosystems engineer and I'm the environmental and design lead.
My name is Joseph Jacobs. I'm currently in mechanical engineering and I'm the safety lead.
Hi, I'm Michael McDonald. I'm a mechanical engineer and I'm the technical lead.
Hi, my name is Maddie Kogachi. I'm a biosystems engineer and I'm the procurement lead.
Hello, my name is Alfani Quintero. I am an electrical and computer engineer and I am the electrical lead.
Hi, my name is Abigail Simon. I am a material science engineer and I am the team lead. Plastic waste is one of the largest global problems, but it could also be one of the keys to solving energy concerns. Last year's team created a system that turned plastic into oil. This year, we are separating that oil into fractions to turn it into gas and diesel.
Our module is compact and transportable. It's under 1,000 pounds. It takes raw pyrolysis oil as input and processes it into different fuel types. These fuels can power water pumps, generators, and other critical infrastructure, especially in disaster-stricken areas where resources are scarce.
This project does more than reduce plastic pollution. It turns waste into life-saving energy. By refining the fuel, we make it more practical for emergency use, providing clean water, electricity, and power where it's needed most. With our work, last year's breakthrough became a real-world solution.
In our round bottom flask, our input is pyrolysis oil, which is a polypropylene plastic that is then heated and compressed into the following product. We will then place it inside of this round bottom flask to then use in the rest of the experiment.
As our system runs and different fractions become condensed through our condenser, the liquid fractions go down this finger and into one of these containers in the cal receiving flask. When we decide that we don't want to gather any more of this fraction, we turn the cal flask and set the output to a different receiving flask. And this continues throughout all four. This spins freely even under vacuum, so that no matter what, we can maintain our environment and collect different fractions. These fractions can be used for different purposes, and most of the fraction that we're getting from the pyrolysis oil is used to make kerosene for lighting and cooking.
So for our project, we finalized down to 3 overall designs. Design 1 is the most accurate. It will produce the fractions that have the highest purity, and it will also produce the most amount of fractions. The problem with design 1, though, is that it is very intensive to make. It takes a lot of chemical engineering, which we do not have one on the team. And it also takes a lot of knowledge about the input of your system, which at the time we had limited knowledge on. Design 2 is also feasible. It is limited by the amount of fractions it produces, but again, you still need to know the temperatures at which the fractions come off at. Design 3 is ultimately what we went with. Something similar, it's not exact, it was just our first overall design, but from our research, we found that this is the best design because you can put in your input into the bottom, and then you can heat it up, and you can monitor at what temperature things start to boil off at, so you don't have to know what temperature to set it at. And then it rises. The Vigoro tower, which is the fractionating column here in design 3, is where that interaction can happen. It can boil up, the things can come down, and those fractions can then separate in the energy exchange. They can go through the condenser, and then you can just manually change the vial, or as our case, the cow adapter, to separate those fractions. The research behind distillation and towers is that the fractions that come off at higher temperatures, as you can see, are your butanes and you're more closer to gasoline. And those have a lower carbon content, but they also come off at a lower temperature. So those will be some of your first fractions. They're usually clearer with maybe a yellowish slight tint. And then as the system increases, you start to see the kerosene and diesel fuels. Unfortunately, we won't be able to get anything beyond that, as our system won't be able to run that high because we want to keep it safe and away from any risks of exploding.
So this is our Arduino. This is our LCD display, where we have our temperature in degrees Celsius. We have our max module amplifiers in order to be able to read our outputs from the thermocouples. Then here we have a buzzer, which is going to be the alarm system for our project. Here we have a switch in order to kill the buzzer in case of an emergency or in case we need to get rid of that noise. And we also have a potentiometer in order to control the brightness for our LCD display. So this is our kill switch, which here it indicates that it is on. And then in case of an emergency, we can turn this off and it will cut the power to our heater.
The first test produced 7 flasks of output oil. Flasks 1 through 3 ended up being very similar, and 5 through 7 were the same from the leftover in the heating mantle. The boiling point temperatures for flask 1 was 19 to 24 degrees Celsius, flask 2 was 24 to 35 degrees Celsius, flask 3 was 36 to 49 degrees Celsius, flask 4 was 49 to 56 degrees Celsius. Those all correspond with fraction 1, fraction 2, fraction 3, fraction 4, and then fraction 5 was that leftover in the heating mantle. The GCMS results for samples 1 through 3 corresponded to the probable compound being propane, but it is most likely that this could actually be hexane. Sample 4 was octene, octane, nonene, nonane, decane, undecane, dodecane, tridecane, etc. And sample 5 had a variety of things because it was just the base input oil that was left over in the heating mantle.
To conclude, the team would like to thank our sponsors, PQ Environmental Solutions, the chemical engineering team, Dr. Ogden, Dr. Brush, and our mentor, Doug May.